Welcome to this revision zone video on calculating activation energy from experimental data and using Arrhenius' equation. So we'll treat this video more of as a tutorial where I will supply you with some questions. You may want to pause the video, work through it yourself and unpause the video and see what you get. And I would definitely encourage that with questions like this because they are quite substantial marks in the exam, 5, even 6 marks in some cases. So I hope this is useful and we'll get cracking. So this is the second video of a two-part video. The first video was on actual manipulation of Arrhenius' equation. So this is a typical question, not a typical exam question, but a typical kind of setup. So you're in this particular one, you're going to do the experiment at various different temperatures, and you're going to measure the rate constant at those particular temperatures. In this case, they actually refer to the rate constant as a unit per second. And in the previous video, we looked at how 1 over time is proportional to rate and therefore proportional to the rate constant itself. So let's get stuck into this question. So the rate constants for a reaction at a variety of temperatures are shown in the table below. Use the data to create an Arrhenius plot and therefore work out the activation energy and the Arrhenius constant. Now, in regards to this particular part, we'll be supplied with a table like so. Now, this isn't necessarily a typical table you'll see in an exam question because they may well have an additional column here in degrees Celsius, and then you've got to convert that to Kelvin as well. So remember, temperature is in Kelvin when it comes to the Arrhenius equation. You've got these values written in standard form. The E here is just a times 10. So i.e. first one would be 4.59 times 10 to the minus 48, for instance. So that's what that is representing, if you're wondering what that is. Now, what you would be expected to do is complete the columns within this table, and there'll probably be a mark per column, nothing huge in terms of number of marks attained. So it's a good time to pause the video and work out our 1 over temperature and our natural log of rate constant, in this case measured in per second. So a good time to pause the video, and I'll go through how we calculated those in a moment. So in this particular case, when we're looking at working 1 over t, it's quite simple. We are just going to write, well, we're not going to write 1 over 150, but we're going to punch that into our calculator and calculate what that is. And we do the same thing all the way going down. But remember, if we are given the temperature in degrees Celsius, we need to add our 273 to get it to Kelvin. So that's going to be really quite important as well that you keep that in mind. The next one is natural log of K. As said in the previous video, you just need to find the natural log button on your calculator, and then we're just going to write 4.59 times 10 to the minus 48. And we write down the value of that here, and we continue that down, going down each of these columns all the way down until we've done those. And you shouldn't really be making mistakes at this point. It's always good to make sure you double check if you've got time at the end of the exam. So you should end up with a table like so, filled out. One thing I'd like to point out here is that all my values are written to 3 significant figures because that's what has been given to me in the table. And again, especially, well, with chemistry throughout, you should be looking at the values given, and they're recorded to a maximum of 3 significant figures. So I wouldn't go any further than that. I wouldn't go to 4 significant figures. I wouldn't try and write exact decimal values here. I want to make sure I'm trying to be consistent as many with these as possible. And that goes for the natural log of K as well. It's minus 109, but that's 3 significant figures, whereas the minus 82.0 is 3 significant figures. I'm not just going to write minus 82. Now, our job here is to now plot these bits of data as shown in the previous video. So just a reminder here, we've got natural log on the y-axis here. I remember they're going to be negative. And then on the x-axis here, we're going to have our 1 over temperature, which is per Kelvin, remember. And I've put in some scales already, some rough scales to plot. It's another opportunity to pause the video, have a go at drawing this graph. And if you can, calculate the gradient for this particular line of best fit that you will have to generate. So hopefully you've had an opportunity to draw the graph, draw the line, draw your line of best fit, that is, and calculate the gradient. So I'm going to show you what I have got. So this is the rough line of best fit I've got. I'm just doing it on here. It's not exactly very accurate, but as accurate as I can make it. And you can see mine go pretty much in a straight line. I now need to calculate the gradient. So you want to take 2 points on your graph, and you want to make those 2 points as far away from each other as possible. It depends on your scale really, but let's say make them far away from each other as possible, and draw in your triangle. So here's my triangle. I don't know exactly what these values are. We'll take a rough estimate as to what they are. So I'm going to calculate from here. I'm going to say that's roughly 0.0025, roughly halfway. Now you'll notice that actually I haven't used that times 10 to the minus 3 on the axes as I did in previous videos, and actually here we've just got our actual values written in decimal form on the x-axis. Therefore, I'm just going to write 0.0025, and hopefully there's no risk of me making a mess of that either. The next value I'm going to say is 0.006, and this is for the x-axis. So that'll give me my difference on the bottom part of my triangle here. And I've decided that this is minus 40 roughly, and this is minus 105. Obviously, you'll be doing it on graph paper, I would hope, and you can have a more precise value for each of these changes. So the next thing I'm going to do is just work out the differences in my change in y and my change in x. So I've written those in blue as follows. So minus 65 on the y-axis and 0.0035 or 3.5 times 10 to the minus 3. And now I'm going to calculate the gradient by calculating it through the change in y and change in x. That comes to minus 18,571.42. Remember, the units for the gradient is Kelvin. If you're not too sure about that, it's worth looking at the previous video. There's an explanation towards the end on why that gradient is Kelvin, but the idea is that this has no units, and this is a per Kelvin unit. So when you work that out using the gradient, you will get a unit of Kelvin. Now you should also know that getting this gradient, this is the gradient, I need to times my gradient by the real gas constant. And I've obviously got this exact number in my calculator still. I'm not going to use the rounded version here. And it's got to be times the negative of the real gas constant, because that's given by the gradient being equal to minus EA over R. So I'm just going to times by minus R on both sides. That gives me 154,000, it's quite a large number, 402.86. Now the units for that would be the activation energy. So the units for activation energy is joules per mole. Tend to give it in kilojoules per mole, so we're going to divide by 1,000, and I'm going to equate it to 3 significant figures. Remember, there should be no negative in front of this at all. I'm just going to write my accuracy there. 3 significant figures. The activation energy is 154 kilojoules per mole. Now, I do have the actual answer to this, and we'll see how that compares, I guess. But if we're anywhere near close to the actual answer I think I've done pretty well considering how I've drawn it. So I'm really not that close at all. The actual answer is 138 kilojoules per mole. But still don't think I'm too far off considering how I've gone about drawing my gradient. But you should be able to get close to that when drawing it on graph paper and more accurately. Well, you can see my gradient was out by a couple of tens of thousands, about 20,000 really there, which would have made the difference following on. However, we're also asked to calculate the pre-exponential factor, so i.e. Arrhenius is constant. So remember, Arrhenius is constant is known as the pre-exponential factor. Now you can see from this graph, I haven't taken the line of best fit to the y-axis, but this is the y-intercept given by the actual answers. It's 1.74 roughly. There is one way I can work this out where I don't need to worry about the y-intercept, which I'll show you in a moment. But 1.74, I would, or 1.73, the exact answer, I would need to do e to the power of natural log a. So to work out a, I would literally need to do e to the power of ln whatever a is, and that being the y-intercept. So I know it's 1.74 roughly. So that's e to the power of 1.74. The alternative to that particular method is to actually rearrange Arrhenius's equation as follows. If Arrhenius's equation is k equals a e to the power of minus ea over rt, I rearrange it so that it's a is equal to the rest, so a therefore becomes k over e to the power of minus ea over rt. And you basically, for a particular temperature, you'll plug in the rate constant from your table, work it all out, and you should get the same, if not the similar, value to the Arrhenius constant or the pre-exponential factor there. So I hope that makes sense. That's the first question out of the way. We're going to move on to a second question. So this is an exam styled question. You can see what I was mentioning before, being given a table. In this case, they're only asking you to work out one of the missing values on the tables just to check that you know what you're doing. And that's 2 marks, 1 mark for each one there. You then use the table as prior. So we've got 1 over temperature here and natural log of rate. So this time they've actually used a rate value, not even rate constant, but we know that that is proportional to the rate constant. So it has no impact on our final result. And they've given you a space to draw a graph here. Word of advice, make sure you're using at least 2/3 of that graph, if not all of it. They tend to give you a specific size, so you can use quite a lot of it. You can use the outer rim or outer edges of that graph paper as well, as worth doing. But they've told you here, once you've calculated these, is to, on the graph axes below, plot a graph of natural log of rate on the vertical axis against 1 over t on the horizontal, the x-axis. From there, you can calculate the activation energy, which is the next part. So this is the typical kind of setup of an exam question. Lots of marks for the graph, up to 4 marks for the graph, so you don't want to be losing marks there. 2 marks here and 2 marks for the actual calculation, so that's 8 marks in total that you could be potentially getting from a question like this. Remember, one of the marks here actually is just to say it's 2 significant figures. If you don't put your final answer to 2 significant figures, you are definitely going to lose an unnecessary mark. So a good time to pause the video and actually have a go at this. Grab some graph paper, have a go at drawing that graph once you've calculated these two, and calculate the activation energy. And in this case, they're given the final answer to, the real gas constant to 8.31 joules per Kelvin per mole, and the final answer to 2 significant figures. So a good time to pause the video. So here's my working out in terms of answers for that particular question. Quite simple in terms of the table, just 1 over temperature. So 1 over 350 for that first one gives me 2.86 times 10 to the minus 3. And minus 4.10 for the natural log of that rate there. You'd be surprised how many mistakes people make just copying down from a calculator, so always worth double checking those values. So the next part is actually drawing our graph. Now I've set up some axes here, might be worth just having a quick look at those. You don't have to start from 0, which I'm sure you know, so I've started at 2.80 and minus 3.00 there, and my values decreasing as we go down. And that's my y-axis. The no unit for this axis, the label is obviously natural log of k as given here. I could say rate, in fact, so that really should say rate. So there we've got natural log of rates corrected, plus I've then gone and plotted using the graph paper supplied. So I've plotted, that's the green kind of crosses, I hope you can see there, along with a line of best fit. Now, in this particular question, although I wouldn't know it at the time unless I read ahead, I'm not being asked to work out the pre-exponential factor. But if I was, this where it intercepts the y-axis, I would do e to the power of that particular value there, and I should get the pre-exponential factor, or you could do it as shown in the previous question. So I've done my line of best fit. I'm going to go and calculate my gradient as before. Now, I've pre-prepared the answers in terms of from the mark scheme in this particular case in the next part, but let's have a look at what we'll get in terms of gradient from my line of best fit here, because I know it will vary slightly. But like I said before, you're going to pick 2 points as far away from possible. Probably 2 sensible points is the main thing on this, and so you can read it off the graph a little bit easier and then calculate the gradient. So I've just read off my graph very carefully. I've picked this triangle here. The only kind of difficult value for me to have read was this one here. I've used 3.215 because it's just between a half square over at the top, and it's 2.90. Take away that value, it's 0.315. That's the blue, the difference, and minus 4.40 to minus 7.00 there, and the difference is minus 2.60. So just as before, I'm going to calculate my gradient, which is the change in y over change in x. And again, this may vary according to your graph. It will probably vary according to the answers, because I have drawn this. Do a better job than that. So it's change in y over change in x. That is equal to my minus 2.60 divided by my 0.315, which equals 8.254. I'm going to leave it at. Now, at this particular point, you should be thinking, hold on, I've done loads of practice questions in the past. If this is in an exam, that looks awfully small. Now, this is the mistake students make. If you look carefully on my graph, I've written times 10 to the minus 3. And I have not accounted for that in this difference here. So this value here, my 0.315, is actually 2 times 10 to the minus 3. And I need to make sure that I incorporate that here. So that changes things for me. So if I just rectify that, as I have now, put my times 10 to the minus 3 into my gradient calculation here and here, that should give me a much larger answer. And it's minus, because it's a minus gradient, negative gradient, 8,253. I'm going to leave it to 2 decimal places. Let's leave it as 97. Okay, I've got the exact value in my calculator, and as before, I'm going to times this by minus real gas constant. In this case, hasn't been given to us. No, it has been given to us. I apologise. Over to the right, it's 8.31. So we're going to go minus 3.15 times 10 to the minus 4 times by my minus 8.31. Make sure that's minus. And remember, you're not going to have a negative activation energy. And I get something quite substantial in terms of a number. It's 68,590. And remember, that's joules per mole. Typically, want to give it to in kilojoules per mole. The question also has told us that we want it in 2 significant figures, which actually, and I could put a plus in if I really want to. I'm not really required, but let's put it in. We know it's not negative anyway. That comes to 69 kilojoules per mole. Okay, so I hope that kind of helps you work out, or helps you understand how to work out the activation energy for from data like this using the Arrhenius equation. Now, before I do finish this video, I want to just show you what the answers actually do suggest. They do have 69 kilojoules per mole, which I've got exactly that to 2 significant figures. However, they've got exactly 69,000 joules per mole, which is unlikely you're going to get from your graph. Times it by minus 8.31, but their gradient is slightly larger than mine, by not a huge amount, but slightly larger nonetheless. And that's why they've got the 69,000 there, and I've got the 68,590. But nonetheless, that would get me all the marks that I need to to get in this particular occasion. Now, I hope this video was useful in helping you calculate activation energy from the Arrhenius equation. If you enjoyed this video, please hit the like button and subscribe for future videos, and we'll see you next time.